we're hugely interested in this Arctic sea ice cover because the Arctic Ocean itself is one of the fastest changing environments on Earth, if not the fastest changing environment.
Velkommen til LU-mini, hvor du får foredrag og intervjuer med forskere fra UiT, rett på øret, når og hvor du måtte ønske. Mengden is i Polhavene en utrolig viktig indikator på klimaendringene. Men hvordan kan en få oversikt over et så enormt og konstant varierende område? Engelskmannen Jack Landy bryter ny grunn med satellittar og maskinlæring.
So I study sea ice in the Arctic mainly. I come from a geophysics background, but I use Earth observation, so satellites orbiting the Earth, to study the changes in sea ice in the Arctic.
Okay, so how does one do that?
Good question. With some difficulty. So we lobby and beg for the space agencies to launch satellites that orbit over the North and South Pole, because a lot of the Earth satellites for communications, for example, don't orbit high enough for us to get meaningful measurements from the Arctic and the Antarctic. So once we have these satellites, we then have to process the signals that we receive from them into something useful. So I typically work with radar. So we're working with very long wavelength radiation, longer than we can see, for example, with our eyes. And then once we receive those signals, backscattered or reflected from the Earth's surface, we have to process them into something useful. In our case, we're looking at sea ice conditions from these signals.
So, in other words, how the police measure cars in traffic controls is how you measure sea ice?
Yeah, so most of the work that I've been doing is with a technique called altimetry, which, as you say, is exactly like what the police do with their speed guns. So when the police are hiding behind a bush somewhere and they're firing their speed gun at you, it's emitting a pulse, and that pulse is then reflected from your vehicle and comes back to them and gives them a recording of the time, which they can convert to the distance that your car is away from them, and they work out the speed from that. And it's exactly what we do with these altimeters, is they're pointed straight down at the Earth's surface. They emit a pulse of radiation, and then that is reflected or scattered back from the sea ice surface or from cracks between pieces of sea ice that are moving away from each other, where we can measure the height of the ocean. And that comes back to the sensor. From that we get a distance measurement, a range measurement to the Earth's surface. And from the difference in the range between the top of the sea ice and the ocean surface, we get what we call the freeboard, which is exactly like we call it on our boats. We have the freeboard, which is the height of the sea ice surface above the ocean level. And then from that, we can convert that into a pretty good estimate of the thickness of the ice. And so we can record spatial variations or yearly seasonal variations in the thickness of sea ice all across the Arctic and the Antarctic.
And you also measure how much ice there is in an area, I would assume.
Yeah, that's kind of the first thing that people want to know, right? So since the 70s, we've had a very good record of the area of sea ice from sensors that can monitor whether there's ice somewhere or there's not. So we kind of know the extent of sea ice. We always talk about the extent of sea ice. We know that pretty well, and we've known that pretty well since the 70s, 80s. But the thickness of the ice has been a lot harder to measure. And the thickness of the ice is just as important as knowing the area of it, because if you know the thickness of the sea ice, you can kind of predict into the future what's going to happen to the area. So in the middle of the summer, when sea ice is melting, thicker sea ice flows will take longer to melt through all the way to the ocean and disappear than thinner sea ice will. I mean, it makes sense, right?
Yeah.
So if we can record the thickness of the ice, then we can kind of make good predictions into the future of whether there's going to be sea ice in a location or not.
Okay, so there are systems in place that measure polar ice and how thick it is. Doesn't that mean that this is solved then? Are you doing something that's new?
Yeah, so for some time we've had these altimeter systems that have been monitoring mainly sea level. They were launched to measure global sea levels and global sea level change, again since the sort of 60s, 70s. And some of these sensors have been used to create estimates for sea ice thickness since the 1990s. The problem has been is that we can do this pretty reliably in the winter months when the sea ice is not melting. The snow on the top of it is very cold. The radar waves that we're using are penetrating down through the snow and reflecting off the sea ice in a pretty reliable way. But in the summer, the snow starts melting, everything gets very sloppy and slushy, just like it is in Tromsø right now. And it becomes very difficult to measure the sea ice thickness reliably. So what I've been doing with my group is working on a bunch of different techniques to try to create a processing chain where we can measure the ice thickness in summer. So trying to make all the dominoes fall consecutively so that we can overcome some of these challenges with observing the ice as it's melting in the summer.
All right. How do you do that?
Good question. So it's taken a long time. I mean, much longer than I'd care to admit. But there's two principal things that are really challenging in the summer. So in the summer with sea ice, the snow and the melting ice tends to pool in these ponds of meltwater that sit on the ice surface. And they're absolutely beautiful to see, but they cause huge problems to us with our remote sensing, with our satellite observations. The first thing that they cause a problem with is that they look very similar to these cracks between pieces of ice where we measure the ocean. And that's a really crucial step in our processing chain for measuring sea ice thickness. So if the top of our sea ice with these ponds looks exactly the same as those places where we measure the ocean, we can't reliably get a freeboard or a thickness measurement. So the first step for our work was to try to overcome that challenge. And the main technique that we used to do that was machine learning or deep learning. And this is where such tools, I mean, AI and deep learning is big news right now. You know, everyone's kind of talking about it with ChatGPT and these other tools. But in science, we're never quite sure when and where it's going to be really useful, where it might not be. And I think in this case, it was particularly useful because we had huge amounts of data, but we had a very difficult time understanding these complex signals. So these deep learning techniques, which can investigate and examine these complicated signals and find patterns in them, is exactly what we needed. So we were able to use this deep learning tool to identify reliably whether we were looking at ice or at the ocean.
And the second thing?
And the second thing was that it's these ponds that sit on the surface causing us all sorts of problems. But in the winter, the sea ice surface is pretty homogeneous. It's pretty uniform anywhere you look, meaning that these radar signals that we're using are scattering from the surface kind of uniformly over them. But in the summer, these ponds kind of act like strong reflectors. So they dominate the signal. And the radar, all it sees is these highly reflecting ponds. A bit like when you see kind of sun glare on the ocean or on a lake in the summer. You're just seeing that really strong reflection. And that meant that the height estimate, the range estimate that we were getting to the sea ice surface was biased. So it was too high because it was measuring the height of these ponds that sit at a low area, you know, in depressions on the sea ice surface. So to overcome that, we spent quite a lot of time developing modeling tools which could essentially simulate how these radar altimeter systems collect their data over sea ice. And by creating these modeling tools, we could then run all sorts of experiments to say, okay, if we had this many ponds, or if the surface was this rough and the ponds would sit in these locations, what would happen to the radar signal? And by doing that, we could kind of work out the patterns between how much meltwater, how many ponds sit on the ice surface, and how biased the range estimate of the radar might be. And then if we knew the patterns, we can then correct for that, just based on those simulations.
Okay, so those darn ponds, they both act as the actual water surface and as cracks. So they just completely makes a mess out of your data, right?
Yeah, exactly.
Yeah.
Exactly.
So, okay, one of the big things about artificial intelligence is that how can we know that this is reliable? So how can you know that your measurements and your process is accurate?
Yeah, that's a good question. I mean, that's the main question, right? It's a bit of a black box with these things. So they may work in inverted commas, but we don't know if they're truly working until we test them. So what we did was we used a lot of classic techniques in machine learning to change. We use some data that we generated manually where we knew what we were looking at. So we used other satellite sensors to look at the sea ice and say, yes, this is definitely the ocean, this is definitely ice. And we split the amount or the proportions of the data that we used for training our machine learning tool versus testing it in different ways. So we kept changing that around, and we found that our results, basically the accuracy of how well we could observe these cracks or the ponds, was pretty even, regardless of which parts of our data set we used for training versus testing. But I mean, honestly, the best way of testing these sort of things is to have other groups, other research groups do the same thing, use the same techniques or try and build on them, try and improve them further, because it's this repeatability that's crucial for us being able to do this.
But you also go out on the ice.
We do, yeah. We go on the ice as well for a variety of different reasons. We have to, for remote sensing purposes, I mean, a lot of the time I'm sitting in my office working with, data sets on my computer, but I need to first understand them, which we can do with data that we collect on the sea ice itself. We also need to validate them, which we can also do with this data that we collect. So we've done different campaigns. For example, I'm flying out to Greenland this summer for the month of August, and we're going to be taking a plane up north, basically towards the North Pole, when we have these ponds on the sea ice surface. And we have a lot of instruments mounted on this plane for measuring the sea ice. And from these instrumentation, which are basically mimicking the satellite just from a plane, we have photographs, we have a laser scanner which can give us like a 3D model of the sea ice surface, and we have a tool which measures the ice thickness. We can then say, okay, when the ice is covered with this many ponds or in these conditions, what does happen to the radar signal that we're getting from the satellite? And we're going to be flying our plane basically under where the satellite is going. So we fly, and then the satellite whizzes overhead at warp speed, way faster than we're flying. But we try and match the same ice that we're collecting than the satellite is seeing. So then from that, we can say, okay, we're interpreting the signals correctly or incorrectly, and why not if we're not? And we can also use these thickness measurements that we're collecting with the plane to say, is our technique to go to thickness from these satellites actually working?
Okay, we talked a bit about what you do, but why do you do it? What do we need these data for?
Just for fun. Okay,
no,
I'm kidding.
We're wrapping up.
Yeah, I mean, it is, of course, a passion for a lot of people who do this kind of research, especially people who do the field-based research. Then it can become a really big passion. But we're hugely interested in this Arctic sea ice cover because the Arctic Ocean itself is one of the fastest changing environments on Earth, if not the fastest changing environment. So there was a science study last year that showed the Arctic itself is warming 4 times faster than the global average. And actually pretty near us here in Tromsø, up in Svalbard, it's warming 7 times faster than the global average. So why is it doing this? We need to figure this out. And one of the main reasons is a feedback mechanism which is caused by this sea ice. So the ice itself in the winter, when it's got snow on it, or even just the sea ice when it's melting, is pretty reflective. It reflects a lot of the sunlight. But when it gets these ponds on the surface, or when it melts away completely, it becomes much darker. So the ocean surface is much darker and it absorbs the solar radiation. And this kind of perpetuates a feedback because if there's less sea ice because more of it's melted because it's darker, then it means it reveals more darker ocean, and you can therefore absorb more of the sun's energy rather than reflecting it away. And we think this is one of the key mechanisms behind this amplified warming, this 4 times faster warming in the Arctic.
Because the more sea ice that melts, the hotter it gets, which in turn melts more sea ice.
Exactly. Yeah, exactly. And so the satellite measurements that we can collect help us to check these type of hypotheses, right? I mean, this is a science hypothesis. We need to test it. And the idea with collecting these sea ice thickness records is that if we can bridge conventionally we've had these ice thickness records just for the winter, so we've been able to observe how much the ice is growing. We also have these satellites, as we discussed, that measure how much ice there is, the area of it. But if we're missing the summer observations, then we can't tell how fast it's melting. And if we can't tell how fast it's melting, then we don't know how much these ponds that sit on the surface or this absorption into the ocean, what rate that actually increases the ice melt. We can't observe the process of sea ice melt. And that's really crucial because for understanding or for projecting how the Arctic and global temperatures might change into the future, we have to model sea ice. We have to use these computer models that simulate sea ice changes. So those computer models are based on our best understanding of the processes that sea ice grows, melts, moves around, changes. But some of those processes, a lot of them have been developed or are constrained by observations, like satellite observations. So what we hope is that by producing these measurements of the ice melting rates in some of the ice thickness changes in summer for the first time, we can use that to calibrate and then improve the processes within these sea ice models and climate models that project future global temperatures.
Exactly. But also, some might say, ironically, one other big advantage of this, or a big interest for this, comes from the shipping industry. How?
Yeah, it's always a bit of a, there's two sides to the story, right? So we'd like that our observations have as big impact as possible in understanding the science of the Arctic. But there's also, of course, a lot of interest in the Arctic because traditional shipping routes, which have to go via lower latitudes, are very long. So between Asia and North America, or between Asia and Europe, for example, these shipping routes are lengthy. And if there was no sea ice covering the Arctic Ocean, then it'd be a much faster way of moving your stuff from these different areas of the world. So shipping companies are kind of looking at the Arctic as a possible way of improving the efficiency and just making their
a brand new shortcut.
Yeah, their migration is cheaper. So that's all well and good, but of course there's still some ice in the ocean, even if it's disappearing fast. And the reason why people are so interested in the ice thickness data is I was talking about the fact that the ice thickness kind of tells you how much ice is going to be somewhere in the future, because the thicker the ice is, the longer it takes to melt through to nothing. And the shipping companies want no ice. So the idea is that maybe we can use these ice thickness data from satellites to tell us, okay, in 1 week, in 2 weeks, in 4 weeks, in 2 months, how much ice is going to be at a very specific location in the Arctic. And for a shipping company that is sitting there kind of planning their summer routes, that's perfect, right? They want to know whether this route that they're trying to take through the Northwest Passage or through the Northeast Passage over the Arctic is going to be viable. And that's good in some ways, because we want to, if these practices are going to go ahead, which undoubtedly they are, if the ice keeps retreating, then we want to make sure they're as safe and as sustainable as they can be. So the best monitoring of the ice and the best observations that they can get, the best forecasting, the safer it's going to be. But on the flip side, I think there's a bit of a lack of understanding, because the sea ice in the Arctic, even if in total the numbers are going down, there's less sea ice area, it's getting thinner, it's also getting more dynamic. So the ice is moving around faster, it's spreading out often very fast, because these thin and less, smaller pieces of ice can be moved around by the wind and the currents very quickly, meaning that shipping companies, for example, or any stakeholder using the Arctic might encounter sea ice in places that they're not expecting. And that might actually be happening more often in some places in the new Arctic than it used to.
The EU thinks that this is interesting too. You got some great news like a month ago, I think. Could you explain that?
Yeah, we this work that we've been doing, that I said is been going on for some time, and to keep supporting it, to keep pushing it forward, we have to apply for funding. We have to keep trying to get it funded. And so myself and others have been writing proposals and talking to different funding agencies about this for a long time. One of the funding agencies that we've put a proposal into is the EU through their European Research Council ERC program, and got some great news last month. We were lucky enough to get a grant funded from the ERC, and that's a 5-year project. So that will be running now for most of the rest of this decade. And the focus of this project is to try to push forward the quality and the latency, how quickly we can get these ice thickness observations in the Arctic, and also to more easily and more quickly get them into the models, get them into the sea ice models, both for the purposes of improving processes of sea ice melt in the summer and hopefully making better projections of future sea ice in the Arctic, and for these short-term forecasting goals, which should support different stakeholders working in the Arctic.
You're being very modest now, because this is, as we say in Norway, a big feather in the hat for both UIT and yourself.
Yeah, no, maybe. I don't know. I don't like to toot my own horn too much, but it's great. I mean, of course, I'm very happy about it, because it's the work that I'm most passionate about doing now has been funded. It also is going to allow us to hire at least 3 people working on long contracts here at UIT towards this goal. So it'll allow me to start building a team working on this, rather than just myself and a couple other people around the world who've been kind of doing it on and off with all our other commitments over the last few years.
Yeah, excellent. You're saying you're very passionate about this and very interested in sea ice, which for us Norwegians, which we like to think of ourselves as, we are the ice and sea loving people. You're British, right?
Yeah.
Yeah. Why are you here? How did this happen?
It's a fair point. That is a fair point. I've been asked this quite often by Norwegians.
I'm not saying that you don't belong here. Is there a story there?
Yeah. So for me, growing up, I would be regaled by my father with stories of work in the Antarctic. So he was he did his undergraduate in the UK, but he wasn't British. He grew up in Switzerland with American parents. So I also have a very large part of my family is in the US. But he grew up in Switzerland and then did his undergrad in the UK, and was one of the first non-Brits working for the British Antarctic Survey in the 1970s. So he kind of got a bit of a buy to work on his master's thesis with the British Antarctic Survey. And he did 2 overwintering campaigns and some summer work in the Antarctic. And his work was focused on snow science, so snow chemistry. And he would tell us all these fascinating stories, while I was growing up, about usually things that had gone wrong. Because in the 1970s, doing work on the Antarctic ice sheet was a little bit, here and there. But it just made, it made me and my brother and sister both, all of us were fascinated by ice and snow. So I kind of always had this passion for it, and I did geophysics and then, really wanted to make sure that if I did research, if I got into science, that I was doing something related to snow or to ice. And in the UK, that usually means getting into glaciology. A lot of people work on Greenland or the Antarctic or in the Alps. But I contacted a group in Canada where I did my PhD, and they were offering a position related to sea ice, which I really didn't have any idea about. It wasn't anything to do with my undergraduate classes. But what it did have was a lot of fieldwork involved. And I was just desperate to go out and spend months on ice somewhere, taking measurements and collecting data. And so that's why I ended up working with sea ice, as I spent 7 years in Canada, did a lot of field work in the Canadian Arctic, which is a beautiful place. And then after that, returned to Europe shortly in the UK before coming here to Tromsø.
Yeah, and here you are part of the CIRFA group. What is that?
Yeah, so we have an Earth observation group, which is part of the physics department. And about 8-9 years ago, one of my colleagues, Torbjørn Eltoft, he led a proposal for a centre, a very large centre, which is called CIRFA, the Centre for, I've got to get this right or Torbjørn's going to kill me, Centre for Integrated and Remote Sensing and Forecasting for Arctic Operations, I think.
Yeah, I'm not going to quote it.
So what the idea of this centre is to use remote sensing to develop new and improved remote sensing techniques with all sorts of different satellites, more than just the ones I'm using, for example, to support environmental monitoring and operations and stakeholders working in the Arctic here through Norway. And it's been a great success. We've had, I think, almost 20 PhDs graduate doing these kind of in these kind of topics, and many other staff members, working on similar tools.
You seem like a good fit in that group.
Yeah, it's good fun.
Yeah.
It's good fun.
Excellent. Jack Landy, thank you so much for coming, and good luck in the future projects.
Thanks for having me.